is Jack Lee, and this is my course presentation for my modern physics course through Texas A&M at Corpus Christi. During this presentation, I'll be covering a brief history of the creation of nuclear weapons, what the term nuclear weapon really refers to, their basic design, what they used as a fuel source, the reactions that they utilize, the power that they are capable of, the effects and dangers of a nuclear explosion, and their development up to modern time. On April 8th, 1945, President Roosevelt called for the surrender of Japan to the Allied forces during World War II. When they denied, he ordered the new weapon dubbed Little Boy be dropped on Hiroshima, Japan. The next day, a single plane flew in high altitude over Hiroshima and it dropped it. 45 seconds later, the bomb detonated and approximately 66,000 Japanese people were indiscriminately killed, with nearly as many being injured. This unveiling of catastrophe would go on to change the nature of war and create the development of weapons that endangered the inhabitants of our planet as a whole. Where did they come from? In the early 1940s, Leo Szilard, a Hungarian-American physicist, recognized the potential of research involving energy release in atoms. After conferring with colleagues and receiving their affirmations, he contacted Albert Einstein, a personal acquaintance of his, and Einstein agreed that he saw a threat to the world, and he wrote a letter to President Roosevelt on the matter. After Szilard met with Roosevelt, he was tasked with discovering the potential for this new energy source and figuring out before anyone else could. Alexander Sachs, Roosevelt's advisor, was allegedly told to see that the Nazis don't blow us up and was put in charge of the matter. The group that was brought together formed what was eventually known as the Manhattan Project, and they went to create the first atomic bomb. What is a nuclear weapon? A nuclear weapon is a device that harnesses the power of atoms to create an explosion. The process used to do such is a fission reaction, where an atom is split into smaller atoms in an explosive exothermic reaction. This reaction requires a certain quantity of material to be present to attain a critical mass, which allows a self-driven chain reaction of fission to occur. Later, fusion would be discovered as a means to produce many times more energy than fission, but the required conditions were much more difficult to attain. The way in which a nuclear reaction occurs depends upon the device's construction. In a gun type, a piece of enriched heavy element, typically uranium, is launched via a conventional explosive into another piece of uranium, causing a critical mass and a chain reaction of fission to occur. In the implosion design seen to the right of it, it uses conventional explosives on all sides to squeeze the heavy element into a smaller critical mass, which initiates the same type of fission reaction. The design on the far right is that of a fusion bomb. It requires a fission reaction to meet the conditions of the subsequent internal fusion reaction. Fission and fusion. As illustrated in the figure, a fission reaction occurs only when a neutron bombardment, when neutron bombards uranium, in this case uranium-235, causing it to split into smaller nuclei. It also releases chemical energy as heat, and it jettisons more neutrons to chain the reaction with other uranium-235s. In a fusion reaction, it uses a lighter nuclei, but requires that they be in a plasma state. This could require temperatures in excess of 100 million degrees Celsius. This is why fission reaction is required to initiate a fusion reaction. The energy released from this reaction is many times greater than that of fission, and the light elements are overly abundant in the world, making this a much cheaper alternative if we could figure out how to do it without the heat. The two processes are similar in that they involve a nuclear change and release energy, but they differ in that the fission reaction releases a deadly radiation while the fusion does not. Fusion reaction is many times more powerful, but the lower output of fission makes it easier to contain. This is why nuclear power plants utilize fission in the reactors around the world. How much power do they create? The intensity of nuclear reactions is so great that a conventional means has to be applied to understand it. Specifically, a comparison to the much more conventional TNT. The ratings given are kilotons and megatons, which are equal to 2 million and 2 billion pounds of TNT respectively. As seen in the figure below, a single uranium-235 atom, when bombarded by a neutron, will split into smaller nuclei, release more neutrons, and also release 170 mega electron volts, which is an astounding amount for its size. When some math is performed, as seen on the right, we see that if this specific reaction were to occur for every atom in a kilogram of uranium-235, it would produce 6.8 times 10 to the 12th power joules of energy, which is a very, very large amount of energy for the amount of fuel used. To put that in a better perspective or an easier perspective to understand, I did a few comparisons for the value of that power. 1 kilogram of uranium-235, if put through that process or that reaction for every nuclei, would produce enough energy to detonate with a force of 32.4 million pounds of TNT. It could also power a common 60 watt-hour light bulb for over 129 billion years that energy could be captured and stored. It's also able to provide enough power for a modern electric vehicle to travel approximately 63 million miles. Or if I converted that much power into my standard electric rate, I would have an electric bill of $2.12 million. With the dangers of a nuclear device, the detonation of the device doesn't do what I listed in the previous slide. Unfortunately, it doesn't power a car or make my electric bill high, thankfully. But when one is detonated, a concussive blast occurs due to the enormous amounts of thermal energy being released, and a shockwave travels out for miles. This shockwave scales dependent on the payload size. It destroys structures and kills any in its wake. And as that's happening, an intense wave of thermal radiation scorches the surrounding area and emits a large cloud into the sky. And this initial blast is also what creates that bright light that's associated with nuclear explosions. As all of this is happening, ionizing radiation also flows out, and it pierces through structures and people alike, causes damage to living tissues and organs over time, causing radiation sickness and death in people that get too high of a dose of it. Lastly, the residual radiation that is left behind is known as the fallout, and it makes it so that the creatures in the area become sick and may succumb to radiation sickness if they're overly exposed. The reason that it's called fallout is because when the initial blast happens, a large amount of dust and debris is blown up into the sky, and it absorbs a large amount of the radiation. And the term fallout refers to it falling back to the ground. Advanced development. Atomic bombs are the originally developed nuclear weapon. They use fission to create an explosion to wreak havoc on whatever the target area is, in addition to all of those other effects that I previously mentioned. Thermonuclear bombs are a fusion reaction which are much more devastating on an explosive scale than their fission counterparts. They get their name from the intense heat required, that 100 million degrees Celsius required to put the uh, hydrogen atoms into a plasma state. The next one, a neutron bomb, refers to a fusion bomb that is designed to intensify the ionizing radiation of a fission bomb to make it better at passing through walls and armor so that it can deliver lethal doses of ionizing radiation to enemy troops or forces that are hidden behind armor or barriers. And it's capable of delivering lethal doses of this radiation without damaging any of the topography. Lastly, the dirty bomb is typically a threat from smaller terrorist organizations more than from another country. This is because the materials tend to be much less refined, meaning that the explosion tends to be much smaller, and the real threat from these comes from that the explosion irradiates a large amount of debris as they're typically designed to, and it'll cause a fallout in that area, which forces the evacuation and could be used to cause mass panic, as it makes that area uninhabitable for a period of time until either enough time has passed for the half-life of whatever is there, or until a very expensive cleanup operation is performed. As seen in the figure, the advent of the hydrogen bomb was a huge difference in power from the shown fission reactions to the left. As you can see, the two bombs dropped on Hiroshima and Nagasaki are shown to the left, and the first hydrogen bomb is shown immediately to its right. And those two little specks to the left were responsible for over 100,000 deaths and nearly as many injuries. So the implications of what that larger blast can do really show that the development of these weapons has taken it to a completely different scale. And using any of these weapons in the current day and age with our even more advanced developments since then could lead to a catastrophe on the global scale, causing potentially a global fallout, or, as was feared during the Cold War, a nuclear winter. In summary, nuclear weapons are devices designed to harness the power of atoms to create an explosion. They wreak devastation through an initial blast, thermal radiation or ionizing radiation, and residual radiation or fallout. They were originally created by the individuals that formed the Manhattan Project and have evolved from fission reactions of splitting atoms to a joint fission fusion for a much more devastating effect. Just to backtrack a little bit, as you can see, the United States first hydrogen bomb had a payload of 10.4 megatons, which is enough to level a metropolis if it was applied to a populated area. And as time progresses, the weapons will become more and more powerful and nefarious in design. And the next step in the design for these weapons will be the development of a way to use fusion without the required fission, so that potentially no harmful radiation will be sent out and it can be contained to just a blast of pure power. Thank you. My name is Jack Lee once again, and that concludes my presentation.